This video serves as an additional illustration of the experiments in the paper. We will present 3 experiments to demonstrate the effectiveness of the proposed metric. The first part is about evaluation of the local scenes. With this experiment, we want to show that the proposed metric is closely related to localization reliability. To quantify the localization reliability of a scene, we define the term PS, which represents the proportion of initial pose where the pose estimation error is below a specific threshold. We choose 4 common scenes and calculate PS value for each scene. According to the definition, logger PS value indicates better localization reliability. We use the different metrics to evaluate the localization reliability for each scene. The evaluation using the QN metric aligns with the PS values, indicating a close relationship between the proposed QN metric and the environment's localization reliability. However, the Qmax metric, which primarily focuses on feature richness, fails to effectively differentiate between scene A and B due to the cluttered structure in scene B, resulting in a higher feature richness and being mistakenly assessed as superior to scene A. In addition, the reason why the evaluation with Qmin, which represents metrics containing the largest eigenvalues, like the condition number, does not distinguish scene B and C well is the introduction of overconservative maximum eigenvalues, which leads to the evaluation influenced by the best observed dimension of the state to be estimated. In this paper, we implement a planning framework that enables robot to make intelligent decisions in selecting optimal topology and sensor orientation. The first thing to show is the simulation scene we create with UE5. A robot has to travel across the Gobi Desert from the town to a warehouse on the other side of the map, relying on a LiDAR with limited FOV for navigation. We compare the proposed method QN with the method Qmax that focuses on feature richness. The main difference between the 2 metrics is that the proposed method QN is concerned not only with completeness of observations but also with accuracy. The structure within the city is clear and the observations are accurate. Therefore, the difference between the 2 metrics is not obvious. However, when outside the town, the planner using Qmax prefers to select weedy areas with cluttered and abundant features, while the proposed QN method prefers to avoid cluttered scenes when the features are enough for localization. The cumulation error during this process indicates that the path planned with QN is more favorable for localization. We also validate the effectiveness of the proposed metric and planning framework in real-world experiment. The robot navigate from start to goal, and only structures within motion capture zone can be used for localization. We conduct 2 sets of experiment, which shows the proposed metric enables the robots to make intelligent decisions by selecting localization-friendly topologies and sensor orientations.